Hi everyone. In this video, we will examine some properties of the Riemann-Stieltjes integral. And in particular, we'll spend some time proving one of those properties in two different ways to observe how different methods of proof can be both beneficial and also not so beneficial depending on the type of claim that we are trying to prove. So today we really want to focus on this theorem 2.45, the algebra of the Riemann-Stieltjes integral. Now, we'll talk through each of these momentarily, but you will see that these first four that I've listed here, some of them look very similar to things we saw for the Riemann integral and also have seen for other things, for derivatives, for continuity, for limits, right? These are all sort of that same algebra, these same sorts of algebra type theorems. But in this particular case, we want to assume we have two functions f and g, both of which are Riemann-Stieltjes integrable with respect to alpha and with respect to beta on some interval AB. So for a little bit of terminology that will be helpful, right, we generally call f and g the integrand, that is the function that is being integrated, and we'll refer to the functions alpha and beta that we're integrating with respect to, we'll refer to those as the integrators, okay? So we have integrals, right? Part of that integral is the integrand. That's the function that I'm integrating. And then now for Riemann-Stieltjes integrals, I have the integrator functions, alpha and beta, these functions that I'm integrating with respect to. Now, I'll point out, right, we're going to, by assuming that f and g are Riemann-Stieltjes integrable with respect to alpha and beta, right, we are assuming that alpha and beta are both monotone increasing functions, right? We are not necessarily assuming that anything beyond that. We're not necessarily assuming that they are continuous, that they are differentiable. We looked at a theorem in the previous video about what happens when alpha is differentiable, but we're not assuming that here. We're simply assuming that f is Riemann-Stieltjes integrable with respect to alpha, f is Riemann-Stieltjes integrable with respect to beta, g is Riemann-Stieltjes integrable with respect to alpha, and g is Riemann-Stieltjes integrable with respect to beta on AB. Further, for this theorem, we're going to assume c is some constant. And then if we have that, we have the following. We're actually going to have 6 claims. We have these 4 and then 2 more. So if we look at the first one, this is a fairly standard sort of claim, right? I can basically pull a constant out of the Riemann-Stieltjes integral. Okay. But again, that says more than this, right? An additional way to sort of think about this is that this is really saying that the function c times f is Riemann-Stieltjes integrable with respect to alpha, since f is Riemann-Stieltjes integrable with respect to alpha. Okay. Similarly, right, this theorem says f plus g is Riemann-Stieltjes integrable with respect to alpha, and that the Riemann-Stieltjes integral of f plus g with respect to alpha is the Riemann-Stieltjes integral of f with respect to alpha plus the Riemann-Stieltjes integral of g with respect to alpha. So again, we've seen these sorts of things before for Riemann integrals, right? This is saying essentially that we can pull constants out of the integrand and we can break up the integral over sums in the integrand, right? So if you've heard of things, if you think of this sort of means the Riemann-Stieltjes integral is a linear operator on some certain set of functions on the set of Riemann-Stieltjes integrable functions. One interesting sort of question is, what is that set, right? We've talked about the fact that, for example, the Riemann integrable functions are a superset of the continuous functions, but we've never really answered the question of precisely what set of functions that is. How do we describe very well the set of all Riemann integrable functions or Riemann-Stieltjes integrable functions? And in fact, that's sort of a hard question, and one we'll actually put off to the follow-up course to this, Math 5620, where we'll as we think about another type of integration called Lebesgue integration, we'll be able to make a little more sense of what the integrable functions are. But nevertheless, again, these first two I think are things you sort of expect. Again, you can pull constants out of the integrand, you can break up the integral over a sum in the integrand. And the proofs of these are virtually identical to the proofs that we did for the Riemann integral, you just end up with some delta alpha k's instead of some delta x k's in the appropriate sums. So we are not going to prove 1 and 2. They're sort of things we've seen before. Now, if we look at 3 and 4, properties 3 and 4 now are about the integrator. Okay, so they sort of, you can think of them as sort of 3 is analogous to 1, but it deals with what happens when the integrator is multiplied by a constant. So here we have, if c is greater than 0, then the Riemann-Stieltjes integral of f with respect to c times alpha is equal to c times the Riemann-Stieltjes integral of f with respect to alpha. So again, one way I can think of this is I can pull a constant out of the integrator, right, and bring it out in front of the integral here. Now, notice that this only really works here when c is greater than 0. That's really because, right, one of our assumptions, if we're trying to calculate the Riemann-Stieltjes integral with respect to a function, one of the conditions of that function is that the function you're integrating with respect to needs to be monotone increasing. Well, we're assuming alpha is monotone increasing. If we multiply it by a negative, that will give us an integrator which is monotone decreasing, which we don't want. Okay, so this restriction here that c needs to be greater than 0 just ensures that this will still be an appropriate integrator function, that it will still be monotone increasing, right? And right, it's true that if I take a monotone increasing function and multiply it by a constant, I do get another monotone increasing function. So again, this is this still works, and now we can pull that c out. Now 4. Oh, so sorry. So if I look back at 1 and 3, right, it's sort of the same property. It's about what happens when I multiply this function by a constant. One deals with what happens when I multiply the integrand by a constant. The other deals with what happens when I multiply the integrator by a constant. The next one, right, number 4, deals with what happens when I have an integrator, which is a sum of two functions. Okay, so here what I have is that the Riemann-Stieltjes integral of f with respect to alpha plus beta is equal to the Riemann-Stieltjes integral of f with respect to alpha plus the Riemann-Stieltjes integral of f with respect to beta. So again, here I can break up the integral over a sum in the integrator, right? Now again, notice that if alpha and beta are monotone increasing, then alpha plus beta will be monotone increasing, okay? The converse is not necessarily true. It is not necessarily the case that if the sum is monotone increasing, that each individual piece will be monotone increasing. So you need to be a little bit careful when you apply this, right? If you want to break this up, you need to make sure you know that alpha and beta are both monotone increasing before you apply this. If they're not both monotone increasing, one of these would fail to be well defined. So again, be a little bit cautious as you're applying this. And again, this corresponds to 2, right? So 4 and 2 are about what happens when we have sums. One deals with sums in the integrand, the other deals with sums in the integrator. Okay? Now, these two are necessarily going to be a little bit different of proofs because there was nothing like this for the Riemann integral. There's no integrator, or the integrator is just the identity function. So we will actually spend some time today looking at a proof of 4. Once we've looked at the other two properties that go with this theorem, we'll spend some time looking at 4 and how we go about proving that. Now, the other two pieces that go here, I've broken off over here. As we discussed when we talked about Riemann integration, I sort of in a way think these are maybe not appropriately placed. That to me, they're not quite so much, or sorry, this last one here is not so much about algebra, especially. But here, this first one just says that if I take some constant between a and b, then I can break up the Riemann-Stieltjes integral from a to b of f with respect to alpha as an integral from a to c of f with respect to alpha plus an integral from c to b of f with respect to alpha. So I can just break up the Riemann-Stieltjes integral into two different pieces, right? And then this last piece is really more of a comparison type theorem. So if f of x is less than g of x on AB, or less than or equal to on AB, then the Riemann-Stieltjes integral of f with respect to alpha must be less than or equal to the Riemann-Stieltjes integral of g with respect to alpha. Okay. So all of these theorems sort of, they're just properties of the Riemann-Stieltjes integral. Again, these are all also true, obviously, for the Riemann integral, right? If we take the case alpha of x is equal to x. So it's not surprising that, again, we see lots of the same ones. But again, we end up with these two new ones that really have to do with properties of the integrator here. So as I mentioned before, we want to spend some time today in this video proving this property here. So before we really get into the proof, right, I just want to emphasize again, there are really sort of two things that are being said here. The first is that this integral exists, right? There's no reason, without having proven anything, to assume that just because f is Riemann-Stieltjes integral with respect to alpha and Riemann-Stieltjes integrable with respect to beta, that it ought to be Riemann-Stieltjes integrable with respect to alpha plus beta. So we need to show that it's Riemann-Stieltjes integrable with respect to alpha plus beta at all, and then once we know that this exists, right, we would need to then know that it's equal to this value, right? Because this is some other value, right? This is not the definition of this, right? So once we know it's integrable, we would then need to show this. Now, as we're going to see, there's sort of two ways to approach this. One is, which is the first one we're going to take, is actually going to sort of show all of this stuff at the same time. So at the exact same time that we can conclude that the function f is integrable with respect to alpha plus beta, we will also get that the integral has to be the integral from the integral of f d alpha plus the integral of f d beta. There's another way to prove it, though, which I've sort of alluded to, which is first just show that this is integrable, and then show that the value of the integral has to be this. We will come back and prove the theorem a second way and show it in that manner. So today what I want to do is just spend some time exploring those two proofs. It'll give us a little more practice working with definitions and theorems related to the Riemann-Stieltjes integral. And will also provide us a little bit of insight into how we make choices about how to prove things, and why in some cases certain methods of proof may be easier, maybe quicker, maybe more intuitive than others. So let's begin with what I'll call proof number one of property 4. Okay. So as with all good analysis proofs, I'm going to take some epsilon greater than 0. Okay, it's going to be arbitrary. And now in this first proof, I'm just going to use the definition of the Riemann-Stieltjes integral. So let's remember, what does that definition say? The definition of the Riemann-Stieltjes integral says a function is Riemann-Stieltjes integrable if the upper Riemann-Stieltjes integral is equal to the lower Riemann-Stieltjes integral, and then the common value of those two is just the value of the integral itself. Okay. So what I want to try to do is I want to try and figure out what the upper Riemann-Stieltjes integral is. I want to try and figure out what the lower Riemann-Stieltjes integral is. And then hopefully those will be the same thing, and that'll be the value of my integral. Okay. In order to do that, I'm going to need to use something about upper and lower Darboux-Stieltjes sums. Okay. So let me start. So what I know is that f is Riemann-Stieltjes integrable with respect to alpha, and f is Riemann-Stieltjes integrable with respect to beta. So since f is Riemann-Stieltjes integrable, and I'm going to use this abbreviation WRT, that just means with respect to alpha and beta, there are going to exist partitions and I'm going to call them P1 and P2. of the interval AB such that the following two conditions hold. So the first condition that holds is going to have to do with the fact that f is Riemann-Stieltjes integrable with respect to alpha. And so what I'm looking at is I'm looking at upper sums. So there exists this partition P1 so that if I take the upper Darboux-Stieltjes sum of f with respect to alpha over the partition P1, I should be able, since f is Riemann-Stieltjes integrable with respect to alpha, I should be able to get an upper sum as close as I would like to the value of the upper integral. Okay, so I have that I should be able to get this less than the upper integral of f d alpha, and I can get that as close as I want. So I'm going to make them within epsilon 2 of one another. Now, if you're not seeing where this comes from, you could sort of see that this would be equivalent to saying if I just subtracted the integral over. Okay, so this is equivalent to this condition here. So remember that the upper integral is defined as the infimum of all upper sums where I take that infimum over all partitions. That means that any particular upper sum must be bigger than the upper integral because the upper integral is the infimum of all those upper sums. So this difference must be positive, but since this is the infimum of all of these things, I should be able to find one of these things. So that's the upper sum using the partition P1 that's as close as I would like to the actual value of the upper integral. Okay. But now the other thing to remember is that f is Riemann-Stieltjes integrable with respect to alpha. I'm trying to show it's Riemann-Stieltjes integrable with respect to alpha plus beta, but I know it's Riemann-Stieltjes integrable with respect to alpha. That means that the upper integral is not just the upper integral, it's actually the value of the integral, right? Because it is integrable, which means the upper integral and the lower integral are equal to each other and are equal to this common value here. So I can actually get rid of those upper integral things. So I can actually find a partition P1 so that the upper sum of f with respect to alpha over P1 is less than the Riemann-Stieltjes integral of f with respect to alpha plus epsilon over 2. And I can do this for any epsilon. Now, similarly, this partition P2, I'm going to choose, this is just basically going to be the partition that works for beta. Okay, so I want to choose the partition P2 so that the upper sum of f with respect to beta over the partition P2 is less than the integral from a to b of f d beta plus epsilon over 2. And again, you could realize this as just being the upper sum of f with respect to beta over P2 minus the integral from a to b of f d beta is less than epsilon over 2. These are equivalent and these are equivalent. All right. So now that I have these two facts, I want to combine them. The problem is they're working over two different partitions. And often the way we resolve this is we take a common refinement of those two partitions. So now I'm going to let P be the common refinement of P1 and P2. So all I'm saying here, right, is that I take all the points in my partition P1, all the points in my partition P2, I throw them all together to form one new big partition, which is a refinement of both P1 and P2, right? To be a refinement just means all the points from P1 are in P. So P is a refinement of P1, and all the points of P2 are in P. So P is a refinement of P2. So we call P their common refinement of P1 and P2. Okay. Now, what I want to do is I'd like to understand the upper sum over P of F with respect to alpha plus beta. I want to try to make sense of what this is equal to, but somehow I'd like to get it in terms of these things. Okay. So the first thing I'm going to do is I'm just going to think about writing out what is this? Like, what is the definition of this? So this would be the sum k equals 1 to n of capital M sub k times delta alpha plus beta sub k. And then I sort of look at that, I think, what on earth is this alpha plus beta sub k? Well, let me come over here for a second. Let me carve out a little bit of space over here to just ask myself, what is this? So if I look at delta of alpha plus beta sub k, what would that mean? That would mean alpha plus beta of x sub k minus alpha plus beta of x sub k minus 1. Okay, well, that really means what? This really means alpha of x sub k plus beta of x sub k minus alpha of x sub k minus 1 plus beta of x sub k minus 1. But then if I match up, this really gives me an alpha of x sub k minus an alpha of x sub k minus 1 minus, I'll get a beta x sub k minus a beta x sub k minus 1. So plus beta x sub k minus beta x sub k minus 1. And if I look at this, this is just delta alpha k. This is just delta beta k. So coming back over here, I realize that I can actually express this as a sum k equals 1 to n of m sub k times. So now what I'm going to do, I'm going to replace this with delta alpha k plus delta beta k. And then I'm just going to break this sum up. And again, this is a finite sum, so I'm okay. And I get this. But now I look at this and I notice, wait, this is just an upper sum over the partition P of F with respect to alpha. This is an upper sum over P of F with respect to beta. Okay. Now these almost look like these, but these are over partitions P1 and P2, and somehow I need to figure out how to deal with that fact. Okay, but for the time being, I have this. Now, let me point out that if you went back and you were, say, looking closely at a proof that you could break up the integrand over a sum. Here we're proving you can break up the integrator over a sum. But if you're looking at a proof that you could break up the integrand over a sum, you would actually have not an equality here. And the problem is that when you have the sum here, this capital M sub k is defined as a supremum. And so you have a supremum of a sum of two things, which is less than or equal to the supremum of f. So you use there this fact that the supremum of f plus g is less than or equal to the supremum of f plus the supremum of g. Okay. So you actually get an inequality in this step here instead of an equality. Now we're able to make it work out. But in some ways, this is actually a little bit easier because here you get a strict equality, whereas when you're dealing with the sum of the integrand, you have an inequality. All right. So let's give ourselves a bit more room and see how we can proceed from here. Now, as we're looking at this, right, remember this quantity, this is an upper sum of f with respect to alpha plus beta. So this is really the thing that we want to keep analyzing because this is the thing that's going to tell us something about the Riemann-Stieltjes integral of f with respect to alpha plus beta. So now that we've gotten rid of some of the important things, we are going to need to come back to some of the stuff I've erased. So what I've done is just popped up a few of those sort of important things that we just proved. And so now, we had already established this. This is how we chose P1. This is how we chose P2. And that last thing we had proven was this. So now working from here, so now what I claim is that this, so remember we said I've got here the partition P. I know something if I had P1 here instead of P. Well, remember that P is a refinement of P1. Okay, so what does that mean? Well, that means if I sort of compare these two right here, right, the upper sum of F with respect to alpha over P, that will be less than or equal to the upper sum of F with respect to alpha over P1. Remember, as we take upper sums, those upper sums, as we take them over finer and finer partitions, meaning partitions with more and more points, right? Those upper sums are decreasing, okay? So in this case, we're sort of moving in the opposite direction. P1 has fewer points than P, so its upper sum must be larger. For exactly the same reason, this second term, right? Again, P is a refinement of P1 and P2. So this term, the upper sum of F with respect to beta over P, must be less than or equal to the upper sum of F with respect to beta over P2. All right, well, now this is great because I know something about each of these, right? So this first term is less than the Riemann integral, or sorry, the Riemann-Stieltjes integral of F with respect to alpha plus epsilon over 2. This second term, right, is less than the Riemann-Stieltjes integral of F with respect to beta plus epsilon over 2. And now if I combine these, right, I get the integral of F with respect to alpha plus the integral of F with respect to beta. And I have a plus epsilon over 2 plus epsilon over 2. So I get plus epsilon there at the end. All right. So what have I proven here? I've found a partition P so that the upper sum of F with respect to alpha plus beta over that partition P is as close as I would like, is within epsilon of this. Okay. So since this holds for any epsilon, it must be the case then that the infimum of all of these things is equal to this. But the infimum of this is the upper integral of F with respect to alpha plus beta. So since this holds for any epsilon greater than 0, then it must be the case that the upper integral of F with respect to alpha plus beta is equal to the integral from a to b of F d alpha plus the integral of F from a to b d beta. Okay. Now, we've shown the upper integral is equal to this. Now we'd like to sort of repeat this argument and show that the lower integral of F with respect to alpha plus beta is equal to this. So we now want to show that the lower integral of F with respect to alpha plus beta is equal to the integral of F with respect to alpha plus the integral of f with respect to beta. All right, now this is going to follow, this second argument is going to follow almost identically to the first. We just will need to swap around some greater thans for less thans. In some particular places, we'll need to switch some plus epsilon over 2's to some minus epsilon over 2's. But the spirit of the proof will be virtually the same. Okay. So again, following a very similar argument, and I'm not going to write all of this out because it's, again, the same. So I could choose partitions Q1 and Q2 of AB such that the lower sum of f with respect to alpha over Q1 is greater than the integral of f with respect to alpha minus epsilon over 2. Now, to see why this is the case, right, you can again here sort of think about an alternate form. Now here, we're dealing with lower sums. And the supremum of the lower sums should be equal to the lower integral. Okay. So what that means is that any particular lower sum is smaller than the lower integral. So this really comes from the fact that if I look at the lower integral of f with respect to alpha minus any particular lower sum, okay. Since this is defined to be the supremum of all these, each of these is bigger, or this is bigger than each of these, but I should be able to get these as close as I would like. Now, if you take what I have written here and you swap some things around, you get this. Okay. And similarly here, we use exactly the same idea, but replace alpha with beta and Q1 with Q2. Okay. So again, these are just coming from the definitions. Oh, and then of course here, right, because I know f is Riemann-Stieltjes integrable, the lower integral is actually just the value of that integral. Okay. So again, same ideas as before, but we're swapping imps for soups, so that necessarily changes the order of some of these things. Okay. All right. Once we do that, we then do a very similar sort of argument. I take Q to be the common refinement of Q1 and Q2. Then I show that the lower integral of, the lower sum of f with respect to alpha beta over Q. Again, I can break up that lower sum in exactly the same way. Using refinements, I can go here. Again, notice that for lower sums, that inequality flips. But that's good because the other inequalities up here were in the opposite direction. And so I end up with this, which again, the conclusion of this all then is that the lower integral of f with respect to alpha plus beta is equal to the integral from a to b. All right, that's the integral from a to b of f d alpha plus the integral from a to b of f d beta minus, or sorry, not minus epsilon over 2, because since this holds for all epsilon greater than 0, then we must have this. Okay. And now once we've established that, right, so then we kind of wrap things up by saying, so if I look at the integral from a to b, the lower integral of f with respect to alpha plus beta, we've now shown here that that's equal to the integral from a to b of f d alpha plus the integral from a to b of f d beta. But we also showed that this was equal to the upper integral of f with respect to alpha plus beta. Okay. So what do I have? I have my lower and upper Riemann integral, or my upper and lower Riemann Stieltjes integral of f with respect to alpha plus beta is equal to each other. Okay. So we can say, and hence, so since the upper and lower integrals are equal to each other, that means that this is integrable. So this exists, and it's equal to their common value, which is exactly the formula we want. Okay. So what I want you to notice about the way we have proven this here, and again, we've proven this just straight through the definition of Riemann-Stieltjes integrability. What I want you to notice here is that we get the integrability and the formula all at the very same time here at the end, right? So what I did is I showed the upper integral is equal to this, the lower integral is equal to this. Okay, great. That means the integral is equal to this thing. So at the very end, I get that this integral exists at exactly the same time that I get that the value has to be this. Now, in this case where we're trying to prove both that something is integrable and we have a formula for that, this is great. I mean, now everything happens at the same time. Okay. I do want to look, though, at another sort of alternative way you might go about proving this. It's not better or worse. It's just different in this case. But in some cases, it may actually be a slightly faster way, depending on what you're trying to prove. So let's now imagine sort of a proof number 2. Okay, and I'm just going to put this up here because a lot of the steps are going to be the same. We're really just sort of reorganizing some of how we're thinking. But what we are going to do is we're going to use a different notion of integrability. So remember that we have the definition of integrability, right? The definition of Riemann-Stieltjes integrability is the upper Riemann-Stieltjes integral and the lower Riemann-Stieltjes integral have to be equal to each other. Then your function is Riemann-Stieltjes integrable. There's that. Then there's also this other integrability criteria, which says a function is Riemann-Stieltjes integrable if you can find a partition so that the difference between the upper sum of f with respect to your integrator minus the lower sum of f with respect to that integrator over that partition, if that distance can be made less than epsilon for any epsilon. So we're actually going to use that first here. Okay, so let's see the sort of alternate proof. So I'm going to take an epsilon greater than 0. Since f is Riemann-Stieltjes integrable with respect to alpha and beta, again, I'm going to use this alternate criteria. Then there exist partitions P1 and P2 such that I can make the difference between my upper and lower sums for f with respect to alpha as small as I'd like. I want to make them less than epsilon over 2. And I can use this partition F2 so that my upper and lower sums of f with respect to beta over this partition P2, that difference is as small as I'd like. I want to make it less than epsilon over 2. All right, now let P be a common refinement of P1 and P2. Then if I look at the difference between the upper and lower sums of f with respect to alpha plus beta over this partition P, well, I can first just use that same property again, that I can break up the upper sum over this integrator function. So if I break those up, right, I can rearrange them in this way. And notice that this gives me sort of all my alpha stuff in this term and all my beta stuff in this term. And then in the next step, I can use the properties of refinements and how refinements of partitions interact with upper and lower sums to get that the second line is less than the third line. So here all I've done is in the alpha terms, I've replaced the partition P with the partition P1. And in the beta sums, I've replaced the partition P with the partition P2. Again, here you're just using the fact that upper sums get smaller as you take refinements, lower sums get larger as you take refinements. But now each of these, right, was defined to be less than epsilon over, or was chosen to be less than epsilon over 2. So each of these is less than epsilon over 2, which is less than epsilon. Now, what have we done so far? So far, we have proven that there exists a partition P so that the upper sum of f with respect to alpha plus beta over p minus the lower sum of f with respect to alpha plus beta over p, that difference can be made less than epsilon, and that epsilon was arbitrary. So for any epsilon, I can find a partition so that this difference is less than epsilon. That means from all of this, we conclude that f is Riemann-Stieltjes integrable with respect to alpha plus beta. Okay. So great, I know this thing is Riemann-Stieltjes integrable, but I don't know what the value is, right? All this tells me is, oh yeah, you can get those upper and lower sums as close as you want to each other. Great, it's integrable. What's the integral? Oh, I don't know, right? So if you're just trying to prove that it's integrable, this is actually a much shorter proof. Okay, it uses a lot of the same ideas, but it's shorter, a little cleaner. It's a nicer proof. But all this allows you to conclude is that f is Riemann-Stieltjes integrable. Well, let's say you had gone through the trouble of proving that. How would you fix the rest of the proof? Well, once you know it's integrable, you just need the value. And to find the value, you could just find the value of the upper integral, or you could just find the value of the lower integral. But you don't need to find both because you know it's Riemann-Stieltjes integrable with respect to alpha plus beta. So either one you compute, they're going to be equal to each other because you already know it's integrable. So now that we have that this is Riemann-Stieltjes integrable, we need to compute that sort of integration formula, but we can basically go back and do the same thing we did before, right, in the first part of proof one, where we show that the upper integral of f with respect to alpha plus beta is equal to this. Okay, so then we just need to do the first part. We just need to deal with the upper sum, right? And once we have this, then we could say, oh, okay, great. Well, I'd finish this off by saying, okay, since f is Riemann-Stieltjes integrable, with respect to alpha plus beta, well, then the value of the integral right, it's integrable. So it's equal to, let's say, its upper integral. And then I would have, if I went back and redid that first part of proof one in proof two here, then I would have that this is equal to the upper integral. Is equal to that. Okay. So what I really want to illustrate here is that when you are trying to prove just that something is integrable, you don't care what the value is, you just want to know that it is actually integrable. Often that alternative criteria that for any epsilon, I can find a partition so that the difference between my upper and lower sums over that partition is less than epsilon. That's often a little bit of a slicker way to prove things. Okay. However, when you actually need to prove what the value of an integral is and that it's integrable, okay, then you often just need to use the definition. Okay, or you're going to have to prove that it's integrable and then do a little more work, which again, this work is often akin to the first half of proving that it's integrable from the definition. You're going to have to do some more work to actually find out what the value of that integral is. So both of these proofs that I've shown you are perfectly valid proofs of this fact, but it's often nice to slow down and look at two different types of proof to assess their strengths, their weaknesses. And again, in this case, I think neither is more efficient than the other. But as we can see, if the problem were turned around a bit, one may very well be a little more efficient than the other, depending on the claim you're trying to prove. That concludes this video. In the next video, we will spend just a bit more time looking at Riemann-Stieltjes integrals with particular emphasis on actually computing a few Riemann-Stieltjes integrals, and looking at a last few properties of the integral itself.